Hi, this is Mingyao, and in this video I'll be looking at how do we characterize a porous media from a CFD simulation. Here I have a plate with lots of holes on it, so it's a grill. And if we were to model geometries like this in all of its detail, it could be very computationally expensive. We need a huge mesh to capture all of the holes here. We've had customers with tens of thousands of holes or nozzles to model. So one way to model this more efficiently is to treat this as a porous media. I'm going to start by creating a unit sector, a unit section for this part. And so let's get started. We'll create a model that looks like this, and I'll extend this by 25 millimeters. And we'll pull this one by 30 millimeters. So I have 25 millimeters on each side of this plate. Then we're going to do the interference check and subtract the solid part. So that's it. We have a couple of small cylinders here. I don't need the grill for my analysis, so I'm going to suppress that, and this will be the simulation geometry. So coming back to Ansys here, we're going to set up a Fluent simulation. So here is the meshing tool. We're going to use a couple of really easy to use meshing controls. One is to turn on proximity. So now by default there are 3 elements to the thickness, and then we want to add in inflation layers to better capture the near wall flow of this structure. Okay, we're going to automatically do 5 layers to the thickness. Since we're using Ansys Fluent, we need to define the boundary names. So I'm using the letter N on the keyboard to call this the inlet. We'll name this the outlet. And then the other 4 surfaces are all symmetry surfaces. And that's it for our analysis. So super easy to set up. We will, I guess I should generate the mesh. Let's go ahead and generate and take a look at it first. Okay. You can see we're resolving the flow through the pipes, the narrow gaps pretty well. So let's go ahead and take this into Ansys Fluent to analyze. It's a pretty small model, so we could use a few cores on my computer to run it. Okay, so the simulation should be mostly set up. The fluid is going to be air. If we double check our cell zone here, right, it's made of air. We have different boundary conditions already defined. We have inlet, we have outlet, we have symmetry. I can display this to look what the symmetry looks like. Inlet and outlet. I guess I should. So that's where the air goes in, and it comes out, and then it goes through this. So we're going to define a velocity inlet. In fact, I'm going to define this as a parameter. So we have a set of input parameters. I guess we can create an inlet parameter here. That could be 0.1 meter per second. We can also create a new input parameter. Right, so call this inlet V for velocity, and it's going to be using this as an inlet parameter. Okay, and then we can create an output parameter. So Right now we don't have any report definitions, so we'll do a surface report of mass weighted average, and we'll call this one of at the inlet of the static pressure. Okay, so we have an output parameter. I probably should rename it to something a little bit more useful, like let's see if we can kind of inlet. Well, we'll call this delta P. Okay, delta OP. Oh, delta P output parameter. Okay. So that's it. Let's go ahead and solve this analysis. We can turn on adjust solver default based on setup, so it does this automatically. Changes some settings. We want to initialize the model, and then let's say run this for up to 400 iterations. We got the residuals here, and we're monitoring the delta P. Let's make sure we set this up to the right location. So this is the inlet pressure. We'll compute it. It's just 1 Pascal, so a very small amount of pressure change. We can take a look at the results quickly here. I'm going to create a plane in the, let's see the mid-x axis. Okay. And we can, for example, create a contour plot on that plane of the pressure. That shows you the pressure. I guess we can also just plot it on the symmetry too. So that's the pressure. We can also look at things like velocity, so how the flow speeds up as it goes through the channels. And that's all we need for our analysis. Let's go ahead and save this. Call this porous media. Okay, so now we should be able to run a series of simulations. Oh, let's do 1 and 10. Update all design points, and it should run my simulations at different inlet velocities. Okay, the first set of simulations completed. I'll fill it in by maybe a couple of extra ones in the kind of the initial part to see what the results look like. Okay, so simulation has completed, and we have a set of data here. So let's copy this data into Microsoft Excel. We'll just do this and copy it over here. So this is V and this is DP. If we look into the Fluent help, we can look for pressure models, pressure porous media models. there are a few of them available. What we're gonna be specifying the viscous resistance. And there's some examples of how to calculate the viscous and inertial resistance. So what we want to look at are these equations here. So we're trying to extract a C1 and C2. So C2 is the inertial resistance factor, and you can see kind of how they calculated it. So C2 is 2 times. So what we do is we turn this into a quadratic equation, and then find the coefficients, and then calculate C1 and C2. So let's go ahead and do that. So what we can do here is I can insert a scatter plot. I guess I should put this in order, or let's just do points here. And we can add a trend line to this. Second order polynomial trend line where intercepts 0, and we want to display the equation on the chart. Okay. So the two values I have here are 22.027 and 19.743. If we look at the equations derived here, this is C2. Where is this? This is the C1 value. So this is the inertial resistance, and this is the viscous inertial resistance factor, and this is the inertial resistance factor. So this is the viscous resistance, and this is inertial resistance. The other information we need here are aside from our coefficients, are the density, the distance, the thickness of our porous media, as well as the viscosity. So let's go in and get all of that information written down. So we need So we need the density, we need the viscosity, and thickness. Okay. So the density, if we go back to our Fluent simulation, so density is 1.225, and viscosity is this value, and the thickness is 5 millimeters. So when we turn something into a porous media, we need the viscous resistance and inertial resistance. Okay. Going back to our documentation here, the inertial resistance is C2, which is the first part, the squared value here. So let's do this one first. So this is try to get it in. Okay. That's equal to this times 2 divided by the density divided by the thickness. And this, the inertial resistance, or C1 here, that's equal to this value divided by the viscosity and divided by the thickness. Okay. So those are my, I think I may have this flipped. Let me double check here. Yeah, I think I have these two flipped over, so how about this? How about we just move this one down here like this? Okay. So that looks better. The viscous resistance is this value and the inertial resistance is that value. Now let's double check our design here. So I'm going to duplicate this. We don't actually want to connect it to the previous model, but that's okay. Delete this connection. And we'll regenerate the mesh, the geometry here. We'll model the area in between the two as a porous media in between the two air sides. We'll remodel our grill as a porous media zone. Run the simulation and see if we get the same results. Okay, so then split this body here and split this body down here and get rid of these 4 sections we don't need. Control C, Control V to create a new part, and then we're gonna pull this up to here. And we're going to make sure everything is meshed conformally, so we don't need to have an interface between these. No more inflation layers. Go ahead and generate a mesh. So much more coarse mesh. Maybe we should make them a little bit more refined. Or let's just go with this. See what the results look like. Oh, I need to make sure the name selections are correct. So let's have the inlet up here, outlet over here, and we need to define this as a porous zone. And symmetry, so and we want to rename this to porous symmetry. Probably should change the mesh a little bit. Yeah, let's go ahead and refine this. Capture proximity. Let's do 5 and see what numbers we get here. Oh, still 5,000. That was tiny. That should be just fine. probably just need one core for this little tiny model. Okay, so it wants me to do this file recorded mesh operations, match zone names. You can't really match it, so I'm going to just say discard. Okay. So this is our model here. We want to, the only thing we want to do is add add a porous media to the cell zone for the porous area. So this will be a porous media. And let's put in our viscous resistance. So the flow is going to be in the y direction, and our viscous resistance is this value, 2.21 e to the 8. And that's, so x is the direction 1, y is direction 2, so we want this to be that. And usually I make the other direction, since we don't want any flow in those areas, to be 2 orders of magnitude larger. And then we want to put in our inertial resistance values. So again, this is that value, and we'll just add a couple zeros to this. And finally, fluid porosity. So let's go to space claim, and we can, for example, measure the area of this. So that's 4 millimeters square, and this area is, let's measure this, 3.214. So what we want here is the porosity. So we want to go to 4 minus 3.214. 216. Let's try that again. 4 minus 3.2146 divided by 4. So that's the porosity, and we'll put that in there too. Okay. And that's it. So we can go ahead and run the simulation. Because everything is linked together as a parameters, we have another set of inlet velocity, and then Ansys will automatically calculate the new delta P. So let's go ahead and let Ansys run through the simulations. Okay, I ran the simulation a couple more times here, got a few more points. You can see that at high flow rates we're getting really good match, but at low flow rates we have less accurate predictions of the performance. That's a big, that's probably due to the way we're doing the curve fitting. You know, we have something out here, and it's we may have some error down near the end here. So to get more accurate performance at low flow rates, we probably want to have more points there. So, or get rid of the 10 here, so that we're not trying to span quite so many orders of magnitude. But this gives you hopefully some idea of if we want to match the flow rates in from 0.1 meter, so 10 centimeters per second to 10 meters per second, we're doing a pretty good job of matching the pressure drop to flow rates. And you can now run a simulation that's many orders of magnitude faster by using this type of porous media approach. As you can see in the Ansys Fluent window, there are many other options and parameters available for porous media. You can do additional corrections to try to span greater ranges and making sure that the results are accurate, so that we have additional options, more advanced models for porous media as needed. But this basic type of calibration can be done very efficiently, very quickly using Ansys CFD. I hope this helps. If you have any questions, feel free to reach out to us. Have a great day. Bye-bye.